calculations that have been carried out for gravitational wave physics to learn something about the dynamics of spinning bodies and point-like spinning bodies. So let me start with a few questions.
You click on the dotted box, otherwise that's going to be.
Oh, that's me.
Yeah.
Got it.
Okay. Right. So let me start with a couple of questions. Okay, I'll start with a couple of questions. So first of all, we certainly know that there exist spinning bodies in nature. So the question is there a relativistic field theory that describes their interactions with gravity? This is not a completely silly question because if one looks at these bodies from far away, then they look point-like. And if you dig through the literature, you will find tons of theorems that say this is really difficult, especially if you want to answer this question quantum mechanically. So we're going to downgrade that. We're not going to solve the go around those no-go theorems. We're going to downgrade that a little bit and ask what about spinning bodies, but we want to describe them as an effective field theory, and we're not going to ask entirely about quantum physics. We're going to ask only about classical physics. And the reason we can do this is that the no-go theorems have not really been studied in the classical regime. So we're going to do this and see if there is a way to go around those theorems in the classical regime. Now, we also know very well that there are very special classical bodies, like the Kerr black hole, very much like the Schwarzschild black hole. So the question, if we succeed in finding something like this, the question that we might want to ask ourselves is if in this description of spinning bodies, there is something different if one wants to restrict to such special objects from a general relativity point of view. So why should we care? Well, like I said, these questions, especially the second and the third, these two, started out in connection with the description of spinning bodies and in general relativity and the gravitational radiation emitted by these things. But there is, of course, just theoretical reason to worry about these. So the main one that I outlined on the previous slide. Now, as I also said, there are lots of calculations that have already been done regarding spinning binaries in general relativity. And even though we don't know what this effective field theory is, at least not in the beginning, we are going to try to leverage that information to learn something about this effective field theory. What we're really going to do is to think really hard about what was done. We're going to write our field theory, and then we're going to compare that with what was done. And I guess you won't be surprised if I already announced that everything matches and we are good to go. Otherwise, I wouldn't really be here talking about this. I'll be talking about something.
Can I ask you, do you provide for a possibility of the spin of the object changing in time or no?
That's a very good question. We should, it's changing in time, not immediately, but we should go back to your question in a little bit. Yes.
I very naively thought the no-go theorem derivation for massless hierarchy.
We're going to talk. We're going to talk about that too. But thank you for the question. All right, so now when we're done with all of this, we're also going to look for structure. As you might have gathered from my talk yesterday, I always like to look for structure because it lets us go forward. And we're, of course, going to look for structure here as well. So here is the goal. There are three: theoretical, practical, and both. So theoretically, we are going to attempt to construct this effective field theory with finitely many higher spin fields, which captures the long-distance behavior, long-distance gravitational interactions of massive spinning bodies. And we are going to try to understand special GR cases. From a practical point of view, the goal is somewhat related to the one yesterday. Start with Newton's potential, generalize it to all orders in velocity for relativistic invariance, as high an order in Newton's constant as we can. Today is going to be just next non-trivial order. And as many orders in spin as we can. We are going to go all the way to 5, which is more than has been done before. And once we have this, we're going to extract some observables, not as fancy observables as we talked about yesterday, but we are still going to talk about observables. And last but not least, we're going to attempt to construct a generating function for these observables. And we're going to see that things that look like page long, they can be obtained from a formula that's essentially half a line. So that's the plan. We're going to talk about higher spin classical particles from a 4-dimensional field theory point of view. We're going to conjecture field theory definition of the Kerr black hole. We're going to show evidence and this generating function that I just described. So again, this is just to set the stage for the kind of information that we're going to use. Of course, we're going to talk about expansions because that's, this is going to be perturbation theory. So there are two of them, the post-Newtonian expansion or weak field non-relativistic, in which everything is expanded in velocity, Newton's constant, and spin. This is most of calculations have been done in this framework. There are a number of calculations which I will review, in which are done in the weak field relativistic framework, in which really the only expansion is in Newton's constant. Now, I should say, on the previous slide, I mentioned that we're going to talk about, say, fourth or fifth order in spin. This is not meant to be understood as an actual expansion in spin, but you have a vector, it's a tag. You can still talk about terms with one of them, terms with two of them, terms with three of them. There is no implication that the spin is actually small in this enterprise.
But just to be clear, when you say expansion and spin, because usually the semi-classical expansion would be large S.
We will have large S. So S will be large, and I will justify in a second why S has to be large. But again, if you have terms with 5 S's, you can always tell them apart from terms with 4 S's. So there's no implication that S is small in any sense.
I guess these are the same questions that Fiona was asking. Normally, again, question from condensed matter. We normally think about quasi-classical expansion and expansion 1 over S.
Yes.
You're expanding in S.
Again, I'm not expanding. I'm just tagging terms with various numbers of S term with S vectors.
Can you expand in 1 over S? Does it exist in this kind of theory?
So S is large. So in principle, yes, it is technically difficult, but in fact, it is as difficult as I can't imagine how to do it in perturbation theory. But in principle, it's not impossible. All right, more questions?
So
Yes.
physically, it's like different powers of S are going to correspond to different types of scattering, kind of like.
It's different. I think of them as different multiples.
Right. Okay.
And physically, this is what these different powers of S are. They're spin-induced multiples. All right, so I do have the requisite slides with credit because credit has to be given where it is due. So there is there are lots of calculations done, like I said, in the post-Newtonian expansion. So this is a typical term in post-Newtonian expansion: some power of S, some power of Newton's constant, and some power of velocity. And the action that has been used for these calculations is, at least we call it a word line action or a word line formalism. It starts like this. This is the action for a point particle, and then there is a spin coupling with the spin connection. And then there are some non-minimal interactions, which I'm not going to tell you for now what they are, but we're going to see what they are in a little bit. They just involve the spin tensor, the spin vector, the velocity, and the metric. So, and this is coupled with general relativity. So there is a plus integral of R. One expands in around flat space. One integrates out the metric fluctuations, and the result is this effective action that describes the interaction of various spins. Then one takes this and solves equations of motion. So there are lots of results that are known, which we're going to match against. There are also a few results dealing with weak field relativistic expansions, but quite a few, quite a smaller number. They go only up to spin square, so just quadrupole moments in spin. And what is going to be the most interesting and important for us is that Justin Vines constructed for us what one might call the Kerr, the stress tensor for the Kerr black hole. Now, you might wonder what exactly is the stress tensor for a Kerr black hole, given that the Kerr black hole is a solution of Einstein's equations with no sources, right? So that sounds like something strange. So what he did was to take Einstein's equations, write them as box acting on a metric fluctuation around flat space equals stuff. He calls that stuff the Kerr stress tensor. you should think of it as the source that you would need to put in flat space to generate iteratively the Kerr solution.
So the horizon.
The horizon starts out as nothing, and then as you iterate it and you resum, you need to resum to get the horizon, but it eventually grows to its nominal size. So we're going to use this. You should think of this really as a form factor. It is literally a form factor. Okay. We are also going to use scattering amplitudes for this for our enterprise. And there is some work about this. And let's review the various proposals that have been put forward. There are 4 of them and a few adjacent and related approaches. So there is the so-called minimal 3-point minimal amplitude. So these people proposed an analog of a field theory analog of this form factor that I was describing. And the goal was to bootstrap that into higher point amplitudes and then loop level amplitudes eventually. There's another approach called exponentiated form factor. It's very closely related. So the idea is that scattering amplitudes have a very nice feature that when you take one massless particle to be very soft, they factorize into something that's universal and something that's not. The stuff that's universal can be resummed into an exponential, and that's what these people did. They made a guess for what that is. It sort of matches that. It has the same problem as these. Now we also have our own proposal, which is what I'm going to discuss most. And then there is also a heavy particle effective field theory that has been put forward. And these people pushed this approach quite a bit. And by the end of it, we are going to be in agreement. So this is all of this is a way of saying that, yes, there are no-go theorems, but something is afoot because everybody is sort of in agreement and nobody actually encounters any particular problems in the classical limit. So let's review the no-go theorems a little bit. So the no-go theorems, they have been really powerful in the sense that we actually don't know of any interacting field theory of higher spin fields with finitely many fields. So because of this, let's talk first about classical physics and then talk about the action. So the classical physics that we're going to confront, we're going to aim for is something that is extracted via the correspondence principle. And this will justify your question about how big is the spin. So the correspondence principle says that all charges have to be large. Spin is one of the charges. So from here, one can immediately guess that it has to be large. But there's another test which is very much related for classical physics, which is that the Compton wavelength of a particle has to be much smaller than that's in separation from other particles. So there are 2 kinds of Compton wavelengths, one that has to do with translation and one that has to do with rotation. So if one just writes that down, then it turns out that the spin, that the side that.
Sorry, you call it Compton, would it be like more like de Broglie?
De Broglie, sorry, yeah, it's de Broglie. Yeah, it's the de Broglie wavelength that has to be smaller than the separation. So if one writes the de Broglie wavelength for rotations, that implies that the spin has to be much larger than 1. This is for rotation. For separation, that implies that the orbital angular momentum has to be much larger than 1. Here, B is the impact parameter. P is the linear momentum of incoming particles, and omega is the rotational velocity. Now, so this implies overall that orbital angular momentum is large, spin is large, and they are all of the order of inverse of the momentum that's being lost by one particle. The reason for this is that B, or the impact parameter, is dual via Fourier transform or Fourier conjugation with the momentum that's being lost. So putting this together, and if you also add to this the fact that Newton's potential is very much classical, one concludes that a typical interaction between 2 particles, sorry, yes.
Sorry, I just want to make sure I understand how you're defining the spin, because I would have thought for a classical particle, the spin is basically just its angular momentum about its internal rotation axis.
That's exactly right.
Oh, okay, yeah, sorry.
That's exactly.
It's not that S has to be bigger, but that S is that. bigger.
S is this, and because of that, this S is big. And yeah, I mean, yes, said differently, we can't really talk about, say, an electron and do what I'm saying for the electron because its spin is, well, it's a half, but it's not, it's a half times h bar. Okay, so putting together, please don't raise your hand, just ask. Right, so if we add to this the fact that Newton's potential is classical, so G over R is classical, we can raise that to any power, it remains classical. That says that the typical, the Fourier transform of a typical interaction between two particles of this type will have this structure. The first part here is the Fourier transform of Newton's potential to some power, the power I. Right? This comes from the measure, and this is just R goes to 1 over R goes to Q. The next factor is of order 1 in the classical limit because of the discussion we just had. So the momentum transfer times spin, the mass is there just for dimensional reasons. So one can add this and still maintain classical nature of this potential to any power. And I didn't say anything about finite size, but if one has finite size here, one adds again R, typical size of the object times the momentum transfer, again to some arbitrary power. This actually relates to the discussion we had last night over dinner about what happens if you add an R to the N operator. That adds more powers of Q, so then one must add some size to the object or some more powers of G to compensate for this. Okay, so to summarize this, I guess I'm speaking a little too slowly. There are a few conclusions that one can draw out of this. One is this is a non-trivial function of G. Therefore, loops, regular loops should contribute in the classical limit. And those loops will contribute in a very particular way. They will contribute only this part, the part of the loop amplitude that depends on the momentum transfer in this particular dependence. Anything else will either be stuff that's obtained from lower orders or stuff that is quantum mechanical, so it shouldn't interest us in the classical regime.
What's the true distinction between like higher order scattering and the loop here, right? It's not a quantum loop.
It's not, it looks very much like a quantum loop, but it's certainly not. Physically, it's not. And if one, so what will distinguish it from, what does distinguish it from an actual loop is that if you look deep inside the calculation, pretty much all matter lines will be almost on shell. And that's exactly what distinguishes them. And we're going to talk only about the one loop here. And I'm not going to emphasize that because it goes deep into the calculation. But this happens to be true pretty much to any loop order that we looked at.
But like in QED, there is a clear distinction between something like tree-level scattering and the loop, right? I mean, like say relativistic corrections and loop corrections, they count pi's differently.
That's right. So
this is all in one class in some sense.
Yeah. So these will not contain, for example, 1 over pi's. Yeah, all the pi's here there will be a little hidden here because normally the coupling is here we usually call it kappa, but in terms of Newton's constant, there are some pi's that are buried in the relation. But other than this, yeah, you are of course perfectly right. And the second conclusion out of little discussion is that we need a field theory with higher spin particles. So this is a justification of the little diatribe in the beginning why we worry about higher spin field theories. So these things are so rare that we have no one available at the moment. There's no quantum one. And the no-go argument, at least the recent version of them, they're based on causality. As you were saying a little bit earlier, most of them have to do with massless particles. I'm sorry, I forgot your name. So most of the current ones have to do with massless particles, massless higher spin particles, but there has been an analysis of massive higher spin particles by these people. And the story goes as follows. Causality requires that the time delay in a scattering process better be positive, right? We don't want time advance, we want an actual time delay. And there is a close relation between the time delay and the eikonal phase of a scattering amplitude. So that's a fancy way of saying that in some limit in which the momentum transfer is low, scattering amplitudes turn out to be exponential. One can understand this just based on that something like this must happen just based on unitarity. M has to be a phase. This is a resound amplitude. M has to be a phase by unitarity. So something like that is not totally unreasonable. And one can argue that this phase is related to the time delay and many other observables in this fashion. So this is like a thermodynamic potential, and it has a bit that's proportional to the energy times the time delay and more stuff. So these guys, following their procedure, looked at this in a little bit more than 4 dimensions, and they concluded that if they want the impact parameter to be arbitrarily small, then there is no non-minimal interaction between gravitons and higher spin particles if they also require that this is positive for every possible polarization of the higher spin particle, and there are quite a few. So this seems like a general argument. There's a little bit of a story to be said about B exactly equal to 4, where there's a logarithm and there's a divergence, so this doesn't exactly apply there, but ultimately, when we do calculations, we still want to regularize in some way. And if we choose to regularize in dimensional regularization, we are going to have to be in this regime. So, yeah.
So, massive U-bolt exists. Surely there's no problem with that at the level of it. So, where are you going to go with it?
Where am I going with this?
Yeah.
So I'm going with this to identifying exactly what the asymptotic polarization of a blue ball is. And that's exactly the one that I'm going to use. So the goal, the possible ways around, we don't get too close and we pick one particular external state. That's exactly where I'm going. That's very good. Okay. That's fair. So classical states. How do we describe higher spin particles? Well, they are usually described by tensors with symmetric indices, and they are traceless, and they're also transverse. Now, there's a little bit of a story that we can add here. If we try to write a field theory that enforces all of these, especially this one, there is a little bit of a complication because one needs auxiliary fields to enforce all of these guys, all of these orthogonality relations. And when we couple that, this has been done, by the way. But if one wants to couple that with gravity, then all the auxiliary fields couple with gravity, and then the action gets complicated. So we're going to simplify our life a little, again, with the idea that we want to describe an object with large spin. And also think that, think about this for a little bit and notice that what we really want is to not allow ourselves to use relations between spin vectors that rely on, say, the finite length of the spin vector. In field theory language, this would be, I would phrase this as, if we were able to restrict ourselves from using that Pauli matrix squares to 1, then we might as well use just spin a half particles and have all multiples at the same time. So with this in mind, what I'm going to do is relax this, and instead of a fixed spin particle, I'm going to have spinning particles with spin from 0 up to spin s. And I'm going to construct a field theory for that. It's still a finite number of spins of states in that year. And it should address this problem while also simplifying our life. So a little bit of algebra. It turns out to be convenient to solve manifestly the traceless condition by going to so-called spinor notation. The details don't really matter. What it ultimately matters is exactly what these states in the rest frame of the particle will be. And from regular quantum mechanics, we know what is a state that actually is classical. It's a coherent state. Right? So we are going to pick these guys to be a spin coherent state, an SU2 coherent state. And we're going to construct our epsilons, our polarization vectors in general, by just boosting this to an arbitrary frame. So this will be our classical state. And it does do what classical physics is supposed to do. It minimizes the standard deviation of the spin. So this turns out to solve our problem. And we're going to get to it sort of clearly solves our problem, right? It has, there's one state, we're never going to get to close enough distance to worry about positivity order by order in the impact parameter. So we already know that we're safe.
Sorry, just conceptual point of view, the classical limit usually when, say can I think of spin in units of h bar quanta? So the S is large, but that's not necessarily a limit of a classical spin. Delta S is also has to be it's not exactly zero, I believe. It has to be usually like the classical limit is like the number of quanta is large and the uncertainty in the number of quanta is much smaller than the number of quanta, but it's also much larger than one.
Yeah, it is
because if
yeah.
I have hundreds of photons over fixed frequency, that's not a classical.
Yeah, no. So delta S will go like square root of S.
Okay, that's
Yeah,
good.
Yeah, that's right. Yeah, delta S does go like square root of S. But it's this ratio that, so the uncertainty is minimized, is of course not set to zero.
Not to zero.
No,
right.
there is actually, there is no real way to set it to zero. Okay, so now what's the relation between these guys that we just constructed and this, these polarization vectors and the actual spin tensors? Well, it turns out that if one plays with Lorentz generators and these polarization vectors, it turns out that to leading order in the momentum that's being lost by a particle, this sandwich of symmetric products of Lorentz generators are just equal to products of spin tensors. So this is our connection between normal formulation of field theory in terms of generators of whatever symmetry group we have, and the classical spins that we want in our classical physics. And the symmetric product here is important because on the right-hand side, this is by construction symmetric, therefore left-hand side has to be symmetric. If we don't enforce the symmetry here, then there will be potentially important terms in here which have to do with turning this product into representations of the Lorentz.
Is this related to the thing you were talking about with the square of the gauge theory amplitude?
It has nothing to do with that.
It looks like you're
Yes,
parameterizing in terms of two vector field.
No, so I'm sorry. Perhaps I should have said this is this object here. So maybe I shouldn't have answered your question as quickly as I did. So this parameterizes a vector in terms of a product of two spinors. So these, I should say, these are, one can think of these size as solutions of the Dirac equation again. But it has nothing to do with writing a graviton as a product of two vectors. There are many vectors in here. I'm parameterizing a totally symmetric tensor as a product of identical vectors that enforces the symmetry. And the spinor part of it enforces tracelessness because in spinor space, the metric is a Levi-Civita tensor. So anything that's symmetric would be also traceless by construction. This is, this is just a convenient technical tool. One could just stick with this and work with projectors on the faceless pieces, but it's more convenient. But thanks. All right, so this is just to state that this solves our little problem. And in case you doubt that this is a reasonable solution because I went too quickly over it or just because I spoke too quickly, there's an alternative argument that uses a totally different approach that reaches the same conclusion. Okay, so now there is, before we actually write down a field theory for any of this, I should say that we are talking about the spin tensor here, and the spin tensor that we constructed was constructed by starting with a spin vector or spin tensor in the rest frame, and we boost it to an arbitrary frame. So that spin tensor in the rest frame obeys a relation like this, just because P is m, 0, the spin tensor is 0 and it has only spatial component. So by definition, our spin tensor will obey this relation. Now, that's not a tragedy. One can, in fact, take an arbitrary two-index antisymmetric tensor and impose a constraint on it and call it a spin tensor. This is known as the spin supplementary condition. This one happens to be one of the more popular ones. It's called the covariant spin supplementary condition. Guess what? Because it's covariant. Now, there's another popular one, which is, I don't know if this is the Newton from 1600s, but probably not. Anyhow, so there is another one which is by, you can see that it's not a covariant one. It is, of course, a relation between them. The problem is, or the slight issue which makes this difficult to use in a field theory, is that the relation is non-local as far as momentum is concerned. And since we want local Lagrangians, we're not going to play with this. And in fact, for exactly the same reason, we're not going to construct a field theory that depends explicitly on the spin tensor, because the spin tensor is also a somewhat non-local one, has one over E. So we're going to have to do better. And it's not really difficult to do better, especially if we start with work of Kriplovich and from Pomeranski from long ago, maybe not so long, 20-some years ago. They wrote for us the stress tensor of an arbitrary spin. And I'm not showing that to you. I'm just going to show you the covariantization of that spin tensor. And it looks like this. This is at least one of them anyway. There are many of them. We're going to get to that. So the letters here, R is the Riemann, Ricci scalar, E is the field line, omega is the spin connection. This is a covariant derivative. G is the metric, phi is our higher spin field, and curly L is this object which depends non-trivially on S, which is a covariant version of why do I keep forgetting this name? Pauli-Urbanski vector. So yeah, so this is a covariant version of the Pauli-Urbanski vector. The Pauli-Urbanski vector usually is epsilon times the Lorentz generator times the momentum. This is a covariant version. So this action is completely covariant. And if one extracts the stress tensor out of it, and again uses the linear version of this operator S, one actually gets the stress tensor of Kriplovich and Pomeranski. It's not obvious that this is so. I will ask you to believe me on that, but we can talk about that if you would like. Now, the other thing that's important to notice is that if one squints at this and one squints at the action that I sort of summarized early on, which is this one, they look very much alike. This is the non-minimal part of the wordline action that was used to derive various things in various post-Newtonian results. So we are sort of on the right track. There is one twist here. We are aiming at this as an effective field theory. So if there are other operators that could be added, they should be added. And here is a large class of them, infinitely many of them. In fact, one of these, just one of these, known as H2, has been considered before, and it has a number of interesting properties. If one adds this to this, up to spin square action, one finds that the gravitational Compton amplitude has a much better high energy behavior than the amplitude for a generic H2. This was called gravimagnetic moment.
Can you remind us specifically what is the M tensor?
Oh, the M tensor, thank you. So the M tensor is just a Lorentz generator in some arbitrary unspecified representation. So it's, just think of it as a big matrix of numbers. It does have special commutation properties, but other than that.
I'm sorry, where is the tensor? The phi is a tensor value field or a scalar value?
Phi is a tensor value field. It's at infinity, phi is one of these guys. It rather is Fourier transform is one of these guys. But other than that, it's a tensor value field. Right. So here are more operators that one can add. Again, this is an effective field, so one should very much consider adding them if they are relevant. And well, here are more operators that one can add. And if one goes through the list of operators with two Riemann tensors, so this is what distinguishes these operators from the previous ones that have two Riemann tensors. If one goes through the list, one can construct a lot more. There is a reason that will hopefully become clear later on why exactly I picked these and not others. But
so
anyway,
just for me,
yeah.
This is an expansion 1 over m.
This is you can think of it as an expansion in 1 over m, though it doesn't have to be thought about it this way. It's really
Or spin
what-
over
it- it-
or
so it's really I'm writing here terms with some fixed number of so here I'm writing terms with 1, 2, 3, 4 sorry, with 4 spins, with at least 4 spins, and then here I'm writing terms with at least 5 spins. So and so on, and this will the class if we want this to exist in the classical limit, having 5 spins will require 5 derivatives. And if I have 5 derivatives, I have to compensate for dimensions. So in a sense, it's a tagging of terms with a number of spins. This induces a number of derivatives, which induces an apparent 1 over m expansion. It's not intended to be a 1 over m expansion. Yeah. The natural object in GR, as you very well know, is really the ratio spin over m, which is supposed to be less than 1. And this is, it will be called A in a little bit, but yeah, that's another reason why m disguise appears. Okay, so right, so again, this is the stress tensor that one gets out of this, and at least to this order, these operators tagged with C and these operators tagged with H, they happen to be equivalent. So one might wonder, why exactly did I tag them? Did I make a fuss about them and added them together when they in fact appear to be inequivalent? Hold that thought for 2 minutes. Right, so this is, as it turns out, if you go through Kripovich and Pomerancy's paper, these are 2 of the form factors they have in there. The other 2, they are either manifestly proportional to a momentum vector. So if this guy is on shell, it's going to be projected out, or with a trace of the graviton, so also on shell is projected out, or with q square. So again, q is the momentum of this graviton. That's called q1 there. But if we have anything that's q squared, that means that in a scattering process, that the 2 matter lines will be on top of each other. So we really don't want these terms in this action because we want the 2 particles to be separated from each other. So this captures pretty much everything that we wanted. And interestingly enough, one can match it against this Kerr stress tensor that I mentioned before, which I'm just writing it for you here. A is again the ratio S over M. And if one does this matching, one finds with these normalizations that these coefficients, the sums here, they're all equal to 1. That's good. Now, as it turns out, this stress tensor and consequently this one after matching has a very interesting and special property. It has a symmetry, which doesn't exist for the general C. It's this symmetry. If you shift the spin by the momentum of the graviton, then this stress tensor happens to be invariant. You can see that in here. And so the derivative really picks out the momentum of the graviton. So if you replace A by Q, the momentum of the graviton, the Levy shift, I will toss it out. So interestingly enough, this was not identified before, or at least if it was identified, it wasn't stated and it wasn't used before. We are going, no, please keep this in mind for the next 10 minutes or so, and we're going to try to make use of this. Right, so again, back to the question, why did I make a fuss about C and H? If one actually goes beyond the form factor and one computes a Compton amplitude, then something interesting happens. So here I'm showing you the Compton amplitude with 2 gravitons of opposite helicities. And I packaged them in some way to actually make them short. So they have a number of structures. The thing that doesn't contain any of these coefficients comes from just the covariant derivative in the action. Everything else is sensitive to the non-minimal interactions. And as it turns out, if we think about it, all of these structures are separately gauge invariant because they have different dependencies on coefficients. Now this one on the free coefficients of the Lagrangian. So this one might appear related to these, but we can vary these 2 separately. And this one will vary almost independently from these. So one might wonder if there's another operator that actually talks straight to this thing and doesn't talk to anybody else. And there is one, but before talking about that one, I guess I hope it's clear why I made a fuss about C and H. right? It's possible. They are no longer separated at the next order. So they have, because of this, they have to actually be put in the action separately. Right, so there is indeed another operator that contributes and affects just this one structure. And that operator happens to look like this. In fact, there's more than one operator one can write, but they turn out to be equivalent. So this is its contribution to the Compton amplitude. It does affect exactly this one structure. So this implies that with the effective field theory philosophy, that this operator should also be included. Looks like you have a question.
I thought earlier on you were just saying you were writing down all terms that were allowed by symmetry.
Yeah. Okay, that's indeed. Why am I making a fuss about this?
So, but like, this one must be allowed by symmetry or
I think that's right.
Okay,
So
why didn't it appear?
Okay, it's because it's for a historical reason, so to speak. So we when we wrote this action, so at the first time around, we wrote this action, and at least I was happy that it was matching what has been used before from a Warline point of view. Now here is the kicker, right? It turns out that from a Warline point of view, all of these are equivalent to these, and they're never written down here, and also from a Warline point of view, these are identically zero.
So in other words, EFT is more general description, and if you cut it,
that is correct. So that was supposed to be my next line with a question: how many free parameters actually describe a spinning compact object? Is it just these that have been used before, or is it more? So thanks for making that point for me. Right? Or is it more? Is it CH and at least to order spin cube also one of these guys? So that's a question to which I don't have the answer, and nobody has the answer.
And this term also has this symmetry that you pointed out.
Yeah, it does. That's good. No, sorry. So this term does not have that symmetry. Remember, that symmetry was happening in a very special limit when all those coefficients were 1. This is yeah. So that symmetry will reappear in the limit in which we take that action, we make it very special. We set these to be 0, those c's to be 1. And I guess you won't be surprised to learn that we're going to conjecture that beyond 3 level, which is this, beyond 3 level, if we enforce that symmetry, we're going to describe a Kerr black hole. So that's the conjecture. We have evidence, and I may show you the evidence, but since I'm quickly running out of time, I figured I should state that. Okay, so let me skip the details of exactly how we do the loop calculations. It's not entirely relevant. It's not entirely relevant. What is relevant is that there is a very systematic way to actually enforce in the calculation and from the very beginning the constraint that we want the particles to be separated and never go on top of each other. What really happens is that what we really want, that all the time there is a graviton that propagates between those lines and between the matter particles. And this is something that can be imposed very early on. So we don't really need to compute a complete quantum calculation, which would include, for example, Feynman diagrams like this. So we don't care about these guys. These guys, we don't care about them because they happen to be quantum mechanical. They don't scale with the momentum transfer the right way. I'm going to show it's this one. There is a piece in this 3 amplitude in which the matter lines are on top of each other, and we really want to toss that out. So, right, so this is a one loop calculation. As it turns out, the non-trivial and the new part is part of these 2 diagrams. So these are not Feynman diagrams. These are, if you wish, effective diagrams. They look like scalar integrals, but they include a lot of stuff from these blobs. These blobs are actually 3 amplitudes. This one is the full Compton amplitude, and these 2 are just the 3-point form factors that we discussed, that we saw a little bit earlier. And by the end of it, this through 5th order in spin, this the non-trivial part of the amplitude contains these operators. So curly E is a contraction of Levi-Civita with velocities, momentum transfer, and the spins. So this is 2 powers of spins and 4 powers of spins. Whenever we have an odd number of spins, the relevant operators are the ones from 1 fewer spin times this curly V. So yeah, these are all the operators that appear through order spin to the through 5th power of the spin. I should have used the word order because it's not an expansion. And you know, they look like something. The coefficients of that look like something. They are all full of these C's and Z's, which I inconveniently did not define for you, but they are all combinations of these C's and H's and D's and so on. So now, what happens if we choose to impose that symmetry? And well, what happens is that out of the various operators we had, some of them get tossed out. The ones that I scratched with red are not invariant under this, at least not in the classical regime. So in this limit, we are going to have fewer operators in this amplitude and therefore in the corresponding Hamiltonian. And we're also going to add an extra technical constraint, which is inspired by the observation from early on that H equal to 1, H2 equal to 1 had to do with an improvement in unitarity or an improvement in the high energy behavior. So we're going to conjecture that a Kerr black hole exhibits this symmetry, at least for matter-matter scattering, and also that it's that the high energy properties of the matter-matter scattering is not worse at 1 loop than it is at 3 levels. Now, this is a strong constraint. The strong constraint because this is a higher derivative theory. You add a few more interruptions, the UV goes to hell. So this is bound to impose some strong constraints, and a priori it's not clear that there is a solution. There is a solution to this. No real surprise. And one of the things that comes out of this constraint is that is the thing that we saw before, H2 equal to 1. And all the CNs, which were C plus H, turn out to all be 1, just as required by 3 level. And then the other H's have some other values. And there are also some relations between the various coefficients of the R square.
Sorry, just on this point, you are requiring that the amplitudes are insensitive to deep UV, right?
That's right. We are requiring that they're not insensitive, that they are not worse than the sensitivity of the 3-level amplitudes.
Okay. It seems reasonable, right? I mean, like it's not a. If it were a true quantum loop of gravity,
yeah, I mean, we don't want anything. We don't want anything to be sensitive to the UV cutoff that we have to put in here because this is just an effective field theory anyway. That's correct. Yes.
But it also is a sort of, low energy scattering of some classical objects that should not be sensitive.
Absolutely. Yes. Mm-hmm. Yes. Okay. So now, as you see here, we have, at least as far as R square operators, we have relations. We don't have things fixed. So how does this work? Are we going to get an amplitude that depends on the things that are not fixed? The answer is no. We are going to find that the amplitude that, all this mess that used to be here, all this one collapses to this thing. None of the remaining coefficients survive in the amplitude. And this is just a signal of the fact that we haven't done a good job at weeding out operators that are equivalent on shell. We haven't even tried to actually do that explicitly because too many R's, too many derivatives, and so on. But the amplitudes are doing this for us. So the conjecture is that this is the thing in the red shaded thing describes the scattering of Kerr black holes up to 5 powers of the spin. Or rather 5 spin vectors, shouldn't call them powers. Okay, so observables. Now this is an amplitude, therefore we have an action, therefore we can proceed to compute observables. There are several ways to do this, and the simplest one is to construct an effective Hamiltonian, and out of that solve its classical equations of motion. related to discussions that we had earlier. At this order, there is no radiation. Therefore, everything is conservative to this order. The Hamiltonian we're aiming for looks like two relativistic particles with positive energy and then some spin-dependent interactions. And in here, it turns out to be important to keep track of. So this is still a Hamiltonian, so it's still an action. It's important to keep track of the fact that the spin is really an operator, so it doesn't commute in a trivial way. So the idea is to start with such an ansatz for our effective action, construct its amplitudes and match them against this. And once this is done, it determines the various coefficients of that Hamiltonian, which we then can read off and use to construct observables. Now, don't be scared. I'm not going to start describing what anything here means. The only thing that I want to emphasize here is that one, the things in here that overlap with previous PN and the post-Newtonian, post-Minkowskian results, they're all good. They all check out. Again, all of this happens for specific values of those three parameters, but they all check out. And two, the other thing that I want to emphasize is that they are short, but not particularly pretty. So in view of the 2 minutes that I have left, let me compress the rest into a statement. All of this can be written in a much more compact way. And that much more compact way is this. At order g to the power 1, if one Fourier transforms the tree-level amplitude and commutes it or takes the Poisson bracket of the result with some operator, then one gets the corresponding observable. And in the case at hand, if one Fourier transforms the tree-level amplitude and commutes it with a derivative with respect to the impact parameter, one gets this momentum. All of these come out of that. And that Fourier transform is in fact pretty simple. And if one takes the spin operator, there's an I missing here. If one takes the spin operator and commutes it with exactly the same function, this one, then one finds, let's see, did I put that? No, then one finds the change in spin. So related to Maxim's question from early on, this is, at this stage, this is entirely a, this change in spin is not a change in the magnitude of spin, it's just a change in the orientation of the spin. At this order, it's difficult to see the change in magnitude because the spin is large, and if you emit a graviton, you're going to, at least to first order, you're going to change the spin by h bar or 2h bar. So this is not, this at this stage is a quantum effect. It's an interesting question. It's an interesting question if somehow that effect that I was describing gets enhanced because, so one could, in here, one could imagine that there's a change in spin at each vertex. So this is large minus h bar, but this is, it flips back to large. So that it's not obvious that there is no enhancement because potential 1 over h bar dependencies in these.
Just, you know, you don't have to need an on-shell gravitons, right? So if you scatter massive, so suppose I scattered, I don't know, 2 massive bodies spinning.
Yeah, 2 basketballs.
Right. Can they kind of redistribute their rotation due to the just the virtual graviton, well, the tree-level graviton exchange? Like can the spin flow from one object to another? The amount of rotation in other words changes on scattering.
Not at this order.
No.
Not at this order. Okay, so I am already 2 minutes over time. So okay, can I take 3 more minutes? Okay, so what I'm showing you here is that this works to that there is a generating function of observables to leading order. There is a generating function of observables to to next to leading order. This is slightly more complicated, and it's not as simple as just a commutator or Poisson bracket. There are some additional things in here. Is this I don't know how to call this. It's sort of a half Poisson bracket in which one takes the derivative with respect to the spin and the angular momentum, and this knows about the non-abelian nature of the spin. But all the same, this is all fairly compact and it produces all the observables. And up to order spin to the fourth where it was checked, there is no check beyond spin to the fourth because there is nothing to check against. There was nothing to check against, and we didn't do the check, though perhaps we should have. Now, this might look like a complicated expression and that there is no hope to resum it. Well, it can be resummed into something, and that something looks like this. So it's not something that you might not think about. Right? If everything here were abelian, and if there were no spin, all of this would reduce to what we're very accustomed to in quantum mechanics, right? So it's an integration of O dot equals commutative of H with O, except that in this case H would be the argument. The interesting part of all of this is that, first of all, we hope that this is correct beyond next to leading order we checked. But the best part of this is that one doesn't need to go through all this enterprise and the higher spin calculations and so on to check whether this is correct or not. All one has to do is deal with this effective field theory, so to speak, this one. All one has to do is take this H with arbitrary coefficients here and construct the eikonal phase and plug it in there and compare that with what comes out from solving the equations of motion from exactly the same Hamiltonian. All this can be done without specific reference to general relativity. In principle, something like that should hold as it stands for, say, QED or anything else that contains particles with bodies with high enough spin. So having said all this, let me conclude. So, and still stay within my time. So what did we do? We constructed an effective field theory for higher spin particles coupled with gravity. It's not a higher spin, it's a tower of them. It's tower spin from 0 to some high spin s, but it's still a finite number. And so we constructed one of these, and this is effective in the sense that we're not allowed to take the particles to be too close to each other. So there is, if you wish, a cutoff in this sense. And also there is when you're supposed to take asymptotic states to be of a specific type. There is one question that we sort of half answered, or at least conjectured, which is what is a Kerr black hole in this description? It's something that has a particular shift symmetry, and it's the scattering amplitudes of two such objects has a particularly good high energy behavior. We are also left with one open question for which I actually don't have a conjecture, which is how many parameters does it take to describe a general spinning compact object? We find 3. In the end, the truth is in general relativity. How many pre-parameters does one need to describe a blob of stuff? And the last question is, does this conjecture that that conservative observables are related to amplitude in this particular way, does this conjecture hold? And that's also not clear, but I hope I emphasized enough that quantum field theory can address spin-dependent questions in gravitational physics, and there is great momentum, and we hope to make more progress in the not-too-distant future on this. Thank you very much.
Or is it possible to relate this shift benefit of black hole in their vanishing style?
That's an excellent question. The answer is I have no idea. We did think about it, but at the moment I cannot say anything definitive about this. Part of the reason is that so for for everybody else, unless you already understand Andrei's question. So when you have a big blob of stuff and you subject it to gravity, it wants to deform. Right? There is a recent result that if you're looking at deformations of this type that are static, that is, if you subject this to a static gravitational field, then then a Kerr black hole does not deform. That means that that there are operators in here. In where? So tidal deformability is usually described by R-square operators. So this means that in this particular framework, there are operators which vanish in the static, whose coefficients, there are operators which vanish in the rest frame of a body, and their coefficients are zero. So the answer to your question is I do not know. These relations presumably will impose or will manifest, will set to zero those operators, those coefficients. We have not been brave enough to start classifying the R-square operators and identify specifically those that could and should be zero and see what happens to them. But yeah, that's an excellent question.
Want to see your reaction. So in condensed matter, for a long time there are problems, let's say, quantum impurities, helium theorems, let's say, that move inside helium-4. And you want to integrate out helium-4 and that with some effective dynamics of helium-3. So that's as helium-4 is like the gravitation. Right? And people are doing it for many years. And in particular, what is known that the result is very much dependent on the temperature of your background. So there are effects which go, qualitative effects which go to zero and temperature goes to zero. So how important for you that the temperature of the gravitational field is zero?
Everything here assumes that the temperature is zero. This is equal to zero temperature. I don't like to guess, so most of the time I do guess. I don't like to guess about things that I don't have a good understanding of. And this is one thing that I don't have a good understanding of. But I'm going to guess that the temperature is not going to play a big role here, essentially because, well, unless the temperature is fairly large. Now, if you ask me to justify what I just said, I will have trouble. Yeah, so can I leave it at that?
Yeah, probably question for the explanation for that is, really it's a generic question. You started with diagrammatic theory, you showed the set of diagrams. And then you said there are constraints, and somehow constraints eliminate some of the terms. What it means that you started with some Hamiltonians with arbitrary parameters that you don't know, and then constraints put some of these parameters to zero or more than that.
So there are several constraints that come into play here. One of them is, let's see. So there is this constraint that I dealt away with, and if one were to enforce this in a Lagrangian, that would require adding a few more fields. I dealt with this by saying that I'm going to relax it, and I'm going to not talk about a single field, a single state, that is a state with a single type of spin. I'm going to talk about an entire tower from spin S all the way to spin 0. So that's one constraint that I dealt with this one. There is this other constraint that's this one. There is this. So for us, we are not dealing with this in any sense because we're picking the external state to have this property, but what happens in the middle, that's for the field theory to deal with.
Right. Does it mean that you start with some Lagrangian Hamiltonian and do perturbation theory in diagrammatic sense?
Yeah.
And then what? There's some unknowns in the Lagrangian, which then you fix, or you generate extra terms by doing perturbation theory.
So okay, so in this sense, it would be both. Mm-hmm. So there are, how should I say this? So as I do perturbation theory to leading order, I have a bunch of terms which look different, but they are physically identical. And as I go to the next order, they stop contributing identically to the physics. And the difference is, so if you're asking where does the difference come from, it is indeed presumably related to a constraint that is present, which is again this one. I don't know if that answers your question at all, but maybe.
If it doesn't, we have to take it offline because we have another seminar by Steve Martin in a short while. And meanwhile, let's thank Radu again.
Here for the massive hierarchy, the trader was real page in the world.
Ask the next.
I remember reading some very recent papers about looking for some symmetry, reason symmetry explanation for zero